Okay, we will continue from the last slide where I have stopped in the middle of the design of the furrow irrigation. Let us go for again our PowerPoint presentation. In the design of furrow irrigation, we discussed about furrow length, optimum length, furrow slope, and then this also. Then we go for the next one. Design of furrow irrigation, length and other things are over. Then these are the recommended lengths of furrows in meters. These are all in meters. These are recommended length of furrows for different soil types, furrow lengths. These are the soil types across. And then for different soil types, furrow lengths, furrow slope. See, uh, furrow lengths and the depths of irrigation. So that means for a given soil type and then for a given slope and for depth of irrigation. Of course, again this depth of irrigation and all depends upon the crop also, no doubt. What is the optimum length? This is the design criteria. We can select directly here. This is one such table prepared. What are the some of the important points you should learn? As the furrow slope increases across all soil types, right? Furrow slope increases. Definitely, your furrow length, irrespective of the irrigation, furrow length also gets decreased. For example, you can see in this here, this for example 300, 350, 370, 390, 380, 270. In this case, here it is not in the clays, almost it is maintaining. It is in fact it is shorter length actually. So 0.05 we are having the shorter length of the furrow, and as the slope increases, the length of the furrow also get increased. That is the right. Okay. So length of the furrows are increasing as the slope increasing. Sometimes it is not always uniform. Sometimes it is decreasing also. Here in this case, okay. So let us take about the clays and then looms and then sands. The clays furrow lengths are maximum, whereas sands furrow lengths are minimum. That means more percolation is there in the sands. That is why furrow lengths are a minimum. Similarly, in the case of clays, the less percolation is there, furrow lengths are maximum for a given situation. Okay. So as far as the irrigation is concerned, suppose the irrigation channel is, for example, 15 centimeters compared to 7.5 centimeters in the same soil, across the slope does not vary much. Okay. And in the looms also, in fact, for lesser slope, for lesser depth of irrigation, the furrow length is small, and then more slopes and then more irrigation, the furrow lengths are greater. Same is also like this. So this is a kind of a chart you can prepare. Prepared already, and you can use it. So then, yeah, design of furrow irrigation. Let us go with a example and then equations. The size of the stream usually varies from 0.5 to 2.5 liters per second in furrow irrigation. The maximum size of irrigation stream that can be used at the start of the irrigation is limited by considerations of erosion in furrows. You may have suitable soils, but you may not have other things that you cannot control, like erosion in the furrows. So you cannot have a very big stream. Overtapping of the furrows and prevention of runoff at the downstream, that is another problem. Not only here erosion at the upstream end, but downstream end you have a lot of runoff downstream. You cannot prevent because all this water goes and settle at the downstream, particularly at the greater slopes. So that is why your stream size is limited. The maximum non-erosive flow rate in furrows is estimated by the following empirical equation. Okay, the average, for example, what is the equation? Just simply 0.60 qm is equal to 0.60 by yes, in which qm is the maximum non-erosive stream in liters per second. It simply depends upon the inversely proportional to the slope, expressed as percent. Okay, so you cannot have a bigger stream if you have a slope is greater. That is the thing. The average depth of water applied during an irrigation can be calculated from the following relationship. This is D is equal to Q into 360 into T whole divided by W into L. Of course, that D is the average depth of water applied in centimeters, and Q is the stream size which you want to select liters per second. T duration of irrigation in hours. W furrow spacing in meters, L furrow length. So these are the design parameters that are considered. Ultimately, average depth of water applied can be given with this equation. Let us take an example actually. A furrow, in this example, furrow 100 meters long and spaced about 50 centimeters apart, all irrigated by a initial furrow stream of 2 liters per second. Then the initial furrow stream reached the lower end of the field in 60 minutes. Okay. Then the size of the stream was reduced and then made it as a 0.5 liters per second. The cutback stream, when it is reduced, it is called cutback stream. It is continued for 1 hour. So estimate the average depth of the irrigation. Here there are two stream sizes. In the first stream, average depth of irrigation by initial furrow stream. That is what? D is equal to, by the formula already discussed, we simply substitute these values and then got 14.4 centimeters. This is the 0.5 Q into 360 into T divided by W into L. 2 is the this one uh, stream liters per second, and 60 the time, so many minutes. Um, so many minutes, and we go there. Yeah, so you can substitute here properly uh, to the first stream. Then this stream is, after this stream it is reduced. Again the same formula you just substitute, you'll get this much, 3.6 centimeters. So net average depth of irrigation is depth to the first stream and then depth to the second stream. So that will combine 17.6 centimeters. Now, before we finish, we will also go back to our FAO discussion. That is FAO documents discussion. We will go there. Just for shape, you can see this is the deep furrows, 20 to 30 centimeters, 15 centimeters, the height. So these are for your idea I am showing. And for this is somewhat a wider, bigger, wider, shallow, but shallow. Sometimes, this is a base 15 to 25. Here it is 15 to 25, but top is 10 times D. Okay. Then this is a double ridged furrow, sometimes double ridged furrow. If the soil is very encouraging, you can have a double ridge. That means by capillary action, the water you can get here. So that type of furrow system also you can have. Of course, these are all implements and all. I don't want to spend some time here, but I want to spend think the area this one, wetting patterns. This is very important because in the furrow method, the most important thing you should consider is wetting patterns. Okay, different wetting patterns in furrows depending on the soil types. For example, you take the sand here, it is going deep, not sideways. So you cannot have ridge wide, sharp ridges you should have in this case. As the soil, texture changes, loam, you can see almost like a ball-like thing it appears. So you can have a reasonably wide ridges here in the case of loomy soils. Similarly, if it is a clayey soils, in fact, the ridge, I mean, this wetted zone increases further. So somewhat overlapping is also there from the side furrow. So that is also, you can say, double ridged things you can put it. So like this, you can have other things also here. For example, you can see double. What is this? Ideal wetting pattern. This is ideal wetting pattern. A small overlap should be there so that more watering to the plants, and that means maximum moisture you can utilize from both sides. You can see the spacing between two adjacent furrows is too wide. Only wedge occupied up to here. That means wetting pattern occupied up to here. But the ridge is here, the root is here. No water is received by this plant. So you should take care of this. You have to reduce this gap. Okay, the ridge width. This is too much. Stream size is too small to wet the ridge. Stream size is too small. You have to increase the stream size here in this case. Then stream size too large. No, almost overlapping is there. So you should unnecessarily wastage of water. Okay. So like this, protection against waterlogging. Sometimes, in this case, for example, if you feel that the soil is not suitable, waterlogging conditions are there, you can put the seed here. Suppose in some soil, sandy soils, there is a problem of water scarcity. The seed can be put middle of the furrow. Here at the middle of the ridge on the top. Here middle of the furrow. So you can meet the water requirements of the plant as per the soils. Characteristics. See, planting in the side of the ridge. See, protection against accumulation of salts. If they feel that salts are accumulated in the, this furrows, then you can say seeds are planted here. So even you can turn this seeding just to face the sunshine, sunny side of the ridge. You can put the things. So like this, there are several such methods you can adopt while doing the furrow irrigation. I think that is I am completing the lecture here for this video. Thank you very much.